When you perform a proof by contradiction, there are two key things that you have to have. The first of them you're going to need with any proof ever, and that is a conclusion. At the end of your proof, you always need to finish with a concluding statement, which will often be no more complicated than a restatement of the claim that was made at the beginning. But with a proof by contradiction, you also need to begin with a negation statement. And remember, the best way to think of the negation is that it is the claim that a counterexample exists. So if the claim that you're originally trying to prove is something like this, there are no positive integers that solve this equation, your negation statement needs to be there exists, or there is at least one example, there exists a pair of positive integers such that this equation is true. If you don't have that negation statement, you're not going to be able to find a contradiction. You can't have a contradiction if there's nothing to contradict. Now, the bread and butter of this proof comes down to factorizing 4p squared minus q squared. This is a little tricky to spot until you've seen it once or twice, but it's the difference of two squares. Even though there are two variables involved, you can still factorize it. So it pulls apart into 2p plus q and 2p minus q. And the next thing I do is a little bit of clever reasoning to try to save me some time. I don't want to go through every possible integer pair of factors that multiply to make 25. There's 3 of them, so it wouldn't be impossible, but I'm lazy. I'm a mathematician. So I notice that 2p plus q is going to be bigger than 2p minus q. And that's not always the case. It depends on the value of q. But in this case, we know that because we've assumed it in our negation, that q is a positive integer and p is a positive integer. And since q is positive, 2p plus q is bigger than 2p minus q. And that means that we've got two factors that are different sizes, and the first bracket is the larger one. So the only case I have to consider is that the first bracket is equal to 25 and the second bracket is equal to 1. When I use those two equations and try solving simultaneously, I very quickly discover that p is 6.5, which flies in the face of the original negation, which is that p was a positive integer. I've found my contradiction and I can finish with a conclusion. As an added bonus, if you were to graph this, so instead of p and q, we've got x and y, and plot the whole thing on a coordinate grid, you get this interesting curve, which is known as a hyperbola. It's the same thing you get if you take a y equals 1 over x graph and rotate it by 45 degrees and then stretch it and squash it a little bit. But what you've proved is that no matter how far you go along this weird curve, and it does go on forever, it will never quite touch any of those lattice points, the integer coordinates along the way. For the next proof, we start with a proof by exhaustion. And there's only 2 marks for this. And one of the marks is literally for going through the natural numbers, the positive integers, which are no greater than 4. In other words, the values 1, 2, 3, and 4, and testing to see if the claim that's been made really is true for each of those. You do not need to show that the claim breaks after n is 4, even though it does. All you have to show is that the claim is true for those specific values. And it is. But unless you want to stop at 1 out of 2 marks, you have to make sure you include a conclusion. It's a proof, it needs a conclusion. It's worth noting that this kind of statement, that a cubic is greater than an exponential curve, is only ever going to be true, if at all, for a limited period, because sooner or later, any exponential function that's an exponential growth function, 1 point something or more to the power of x, will always overtake any polynomial function, including cubics. So x cubed might be bigger than 3 to the x for very tiny values of x, but as soon as x gets big enough, then the exponential curve will overtake. Let's look at the second question now. The second part of this was asking us to prove that given that m cubed plus 5 is odd, show that m is even. In other words, if m cubed plus 5 is odd, if this condition is met, we need to demonstrate that necessarily that means m has to be an even number. Well, the negation to this is that there is a counterexample. In other words, a value of m where m cubed plus 5 is odd, and yet m is not even. It breaks the result that is claimed. So that's what my negation looks like. Assume there exists an odd m for which n cubed plus 5 is also odd. So we still need m cubed plus 5 to be odd, but we're claiming there's an odd value of m that makes that true. And if there is, well, we get into the proof by setting m to be equal to 2k plus 1, a generic odd number. And then all we have to do is expand this using a bit of binomial. So it's a bit messy. Some people might do a bit of working out down the right-hand side of the page to make sure they expand this out carefully and properly, and then write the neater, simplified version in the middle. But when you put it all together, we discover that we end up with something where 2 can be pulled out as a common factor. And that's where our contradiction comes from. Again, if you don't have a negation statement, you can't find a contradiction because you've got nothing to contradict. So don't forget to include the negation. Then you'll be able to find a contradiction and finally finish with a conclusion. Now, partial fractions. In both of these questions we're going to look at, the format of the question is provided for you. You just have to be very careful whether or not a is given as a single value like this. So you need to think of it as a divided by 1 perhaps. Make sure you're careful that you can add these carefully so that you get the same denominator as the fraction on the left-hand side. If you need to, use an extra line and write out the fractions in full. But what I tend to do is write out the numerators I would end up with. A needs to be multiplied by both of the brackets because its denominator that you can't see, a over 1, the denominator doesn't share any factors with the denominator on the left. B only needs to be multiplied by the 1 minus 2x factor, and C only needs to be multiplied by the x minus 3 factor. And now we work out the values. Now there are 2 nice values of x that you can sub in. One of them cancels out the x minus 3 bracket every time it appears, and the other one cancels out the 1 minus 2x bracket every time that one appears. But there are no nice values that give you a without also giving you b and c in the equation. So there's a couple of options. You can either sub in something different. A lot of people would use x equals 0, and that will give you an equation linking a, b, and c, but you know b and c, so that's not the end of the world. Or you can compare x squared coefficients, which means we look at the left-hand side, we notice that the number of x squareds is minus 6, and we look at the right-hand side. The only place we're going to get an x squared term is from this first bit, because that's the only bit that's quadratic. The rest is b times something linear, c times something linear. And if we do a times x times minus 2x, we get minus 2ax squared. We compare that with a minus 6x squared, and that tells us that a has to be 3. As the verification step for something like this, I'd highly recommend you get used to using the calculator. You can either substitute in a single value, or you can go the whole hog and use the table mode. Go to menu option number 9 on your calculator and type in for the first of the 2 functions you're allowed, the left-hand side, type in the right-hand side for the second one, and then it'll give you an automatic set of numbers that we can immediately see. F of x and g of x, the left and right hand sides of my so-called identity, are identical for all the values for which they're defined. So although it's not a proof, it's certainly pretty convincing. And if, like me, you make a mistake the first time through, then this is how you'll find out that you have, and you can go back and fix it. For the second question, it's very similar, but this time we have repeated roots in the fraction. So we need to make sure we multiply the top and bottom of this first fraction by another 5x add 2 bracket, as well as a 1 minus 2x bracket. The b fraction needs multiplying only by 1 minus 2x, so that its denominator will match the original one. And c needs multiplying top and bottom by 5x add 2 squared, so that its denominator matches the original. Once you've done that, you can write out your numerator only, if you like, for both sides, if you're confident with that. And then once again, we're looking for the clever values of x to substitute in. And in this case, subbing in a half cancels out the a and the b terms. Subbing in minus 2/5 cancels out the a and the c terms. But there is nothing that will cancel out the b and the c terms without also cancelling out the a term. So you're going to have to bite the bullet and sub in something like x equals 0 and create for yourself an equation linking a, b, and c. But you have b and c, so you can use that to find a. Alternatively, we could compare x squared coefficients again. Not quite as simple as last time, because x squared terms on the right will come from 2 places now. A times 5x times minus 2x, that'll give you minus 10a x squared, and c times 5x times 5x, which will give you 25c x squared. On the left, we've got 50x squared, so we equate the coefficients, the numbers in front of the x squareds, and then we use the fact that we know c is 2, to simplify this equation into something even nicer. and therefore we find the value of A. And at the end, we can write this out more simply if we like, and you could use the trick with the calculator to verify your answers as well. The only other thing I want to mention with this is that if you get nasty numbers for A, B, or C, it's always worth double checking. Be a little suspicious, because in an exam, they're almost always going to give you nice small integers, just like the examples that you can see here.